Hello, this is Calculus 1, and this lecture is on section 2.4, which is all about what's called the chain rule. And the chain rule is a new differentiation rule. So again, differentiation means finding a derivative. So it's a new rule for finding derivatives. And it's a rule that's used for what we call composite functions. So before I talk about composite functions, I'm just gonna show you one, and then I'll kind of talk about what they are. So like, let's say we have a function like this, y equals 3x plus 4 quantity squared. Now, like looking at this function, I recognize that that square means that I'm multiplying 3x plus 4 times 3x plus 4, right? And so let's just say I wanted to find the derivative of this function. I could find the derivative of this by using the product rule because I have a product there, 3x plus 4 and 3x plus 4. And so I could like think of the first 3x plus 4 as like my first function, like we'll call this our f. And then I could think of the second 3x plus 4 as like the second function, the g. And then reminder, the product rule, I'll just write it off to the side. Product rule says that if you're taking the derivative of a product, f times g, that's going to be equal to the derivative of the first function times the second function plus the first function times the derivative of the second function. So this is the product rule. So if we use, again, f equals 3x plus 4 and g equals 3x plus 4. The derivative of f I know is 3, and the derivative of g is also 3. So again, the derivative of a constant is just 0. So that's why I'm like not putting anything for the 4, because the derivative of 4 is 0 since 4 is a constant. So and then just using the product rule here, I would get that y prime is my f prime. So my f prime, which is 3, times my g, which is 3x plus 4, plus my f, which is 3x plus 4, times my g prime, which is 3. And notice what we get here. We can like work through this a couple of ways, but I want to leave it a certain way. What I want to do is I just want to, and I know this is kind of strange, but this is just, we're just going to come back to this later. I want you to notice that we have we have like terms here. So we have 3x plus 4s plus another 3x plus 4s, and we can combine those and we end up with a total of 6 3x plus 4s. So, and I'm just going to leave it like this for now, which I know is really kind of strange, but we'll come back to it, and you'll see why I wanted to leave it this way. So so yeah, if we have like a some function, in this case squared, we can recognize that a square is the same thing as multiplying the function times itself, and then use the product rule. Where the chain rule really comes in handy is if, let's suppose I had something like this. y equals 3x plus 4 raised to the power of 100. So like looking at this, I'd be like, okay, well, this is 3x plus 4 times 3x plus 4 times 3x plus 4 times 3x plus 4 times, and I'm running out of room, right? I'm gonna have 100 of these 3x plus 4s. I'm just gonna stop, because I'm not writing out 100 3x plus 4s. And then, like, even if I did like have the will to write out 3x plus 4 100 times, I would still like then have to use the product rule on that, like over and over and over and over, like, because there's just a bunch of products in there, and so that would be a mess. So instead of doing all that, what we do is we use the chain rule. And what I was saying at the very beginning is that the chain rule is used for what we call composite functions. And composite functions are functions where you have a function within a function. So a composite function will look like this: f of g of x. F of g of x, composite function. So that's again where you have a function within a function. And whenever you have a situation like this, where you have a function within a function, you can use what's called the chain rule. So I'm going to explain in a moment how this right here is a composite function. But before I do that, I'm going to actually write out the chain rule. So the chain rule just says that the derivative of f of g of x is equal to f prime of g of x times g prime of x. And this is the chain rule. And so this is another one of those rules on that long list of derivative rules in that handout from last week's lecture. So this is just another one of those rules. And notice it's like set up like to indicate that you're working with a composite function, derivative of f of g of x. So that said, let's look at the function that I just wrote earlier, 3x plus 4 raised to the power of 100. The way I would think of this as a composite function, this y equals 3x plus 4 raised to the power of 100, is I can look at this and think of this as like all of this right here. I can think of this as like x raised to the power of 100. And I'll just name this function f of x. And then, but notice it is not x raised to the power of 100. It's actually 3x plus 4 raised to the power of 100. I just stuck that x there. But reason for that is to recognize that we can think of this 3x plus 4 as being like an inner function, as like taking the place of that x. And so we can think of this 3x plus 4 as being the g of x in this composite function. And so that said, we can say that f of g of x in this case is 3x plus 4. So think of the 3x plus 4 as like your g of x. and then raised to a power of 100 if you think of your f of x as x to the 100. And so just applying the chain rule here, I would say for this function that the derivative of my f of g of x, or in this case, the derivative of 3x plus 4 raised to the power of 100. Ugh. Hold on, let me get myself my stylus, get my stylus together. So what the chain rule says is that the derivative of this thing, you're going to look at it as kind of like a blob raised to the power of 100, and then apply the power rule. So it's like, okay, I have this thing raised to the power of 100. This thing raised to a power, I use the power rule. And so you go ahead and use the power rule. So that's the bring the power down, just like we've been doing with previous problems, right? We bring that power down and we get 100 times 3x plus 4, and then take 1 away from the power. So raise to the power of 99. So I just used the power rule here, that the derivative of x to the n is n times x to the n minus 1. And then once you've done that, the chain rule says you're not done, because I don't just have x to the n. I have all this other stuff raised to the power of n. And the chain rule says, so notice the chain rule, it says, okay, take the derivative of that big function, which is oftentimes referred to as the outer function or the outside function. And then multiply that by the derivative of the inside function. Whatever was there instead of an x, so we just used the power rule, but we used it for a function that wasn't x raised to a power. It was 3x plus 4 raised to a power. So like we had this other stuff raised to the power. And so the chain rule says, okay, go ahead and use your power rule. But if you had something there other than an x that was being raised to a power, you have to multiply by the derivative of that other thing. And so in this case, we had a 3x plus 4 being raised to the power, not an x. And so I have to multiply by the derivative of 3x plus 4, which is 3. So this right here, this is this part. Oh, sorry, of the chain rule, that g prime of x. So, and then just simplifying this, notice that here we end up with 3 times 100, which is 300. And then times 3x plus 4 raised to the power of 99. And this is our actual derivative. It's right here. So let's go back to the very first problem that I was looking at, where we had like the square. So just going back to this first problem, finding the derivative of 3x plus 4 squared. If I use the chain rule, I get to go ahead and bring this 2 down, because I'm like, okay, this is a blob raised to a power. So I go ahead and use my power rule. So this is 2 times 3x plus 4 raised to the first power, as we take 1 away from the power. And I just want to write that 1 this time just to make sure it's clear. But then the chain rule says we have to multiply if we had anything other than an x that we were raising to a power, which we did. We had 3x plus 4, not just an x. The chain rule says, okay, now you have to multiply by the derivative of that thing that wasn't an x, which in this case is 3x plus 4, and the derivative of 3x plus 4 is 3. And then notice if we multiply the 2 times 3, we end up with 6 times 3x plus 4. This is our derivative right here. And notice it's the same thing we got when we used the product rule right here, which is why I wanted to leave it in this form. Just to be able to recognize that it's the same thing. So, and if I were to use the product rule on on the function that we did before, 3x plus 4 raised to the power of 100, I would actually end up with 300 times 3x plus 4 quantity raised to the power of 99. So really, really cool, this chain rule. It can save you a ton of time. And also, it's just sometimes just necessary to use. Like sometimes you don't really have a choice. So like in this case, we did actually have the choice. We could multiply 3x plus 4 times itself over and over and over 100 times, and then keep using the product rule over and over and over, and just like be working on it for days. But we don't have to do that with the chain rule. So we have the choice to use the chain rule, but sometimes you just have to use the chain rule, period. So if this was confusing, you are like most people, because the chain rule, it can be like really confusing, because I think the most confusing thing about it is it's like really easy to forget to use it, because you just kind of like naturally start using your differentiation rules, and the chain rule, it's just kind of like oh yeah, there's I don't have just x to a power, I have all this other stuff to a power, and it's kind of easy to forget that. Also, you use the chain rule for like any of the rules. Sorry. So in this case, like we use the chain rule for the, like in conjunction with the power rule, but you can use it with like the other rules that we've looked at so far too. So all that said, I'm going to like make a little chart, and hopefully this will help make this less confusing to you. I'm going to make a little chart with like our like regular rule, like our various derivative rules, like kind of like the regular version of the rule, and next to it put the chain rule version of that derivative rule. So like every differentiation rule has like a chain rule version, a chain rule equivalent, except for like the product rule and the quotient rule. Those are kind of like used in other ways in conjunction with the chain rule. But like the power rule, for example, this right here, this one that we just looked at, you're going to use the chain rule version of this if instead of x to the n, you have some function that's not just an x raised to the power of n. So if you have some function, which is oftentimes referred to as the inner function with composite functions, so you have some function raised to a power, some function other than x raised to a power, go ahead and use your power rule. So bring that exponent down, take 1 away from the power, but then the chain rule says to then multiply this by the derivative of whatever that inner function was. That's what the chain rule tells us to do. So, and so I'm going to list the differentiation rules that we've learned so far and write their chain rule equivalent. So like the derivative of e to the x is just e to the x. The chain rule equivalent, so by the way, chain rule is always used whenever you're using a rule but there's some function other than just x in place of the rule. I'm sorry, in your in place of x. So with all of these derivative rules, we'll be using the chain rule whenever we have, instead of just an x where we would normally have an x, we have some function, which we refer to as g of x, or the inner function. And what the chain rule says is that, okay, go ahead and use your rule for like the derivative of e to the x is e to the x, but then you do not stop until you multiply by the derivative of the function that's in the place of x. That's in the place where x normally is, multiply by the derivative of that thing. And again, that function is oftentimes referred to as the inner function. So I haven't written that. I'm gonna just take a moment to write that. So where did I write composite function? Here I did. So what I was saying earlier is just that the g of x is oftentimes referred to as the inner function. And then the f of x is referred to as the outer function. And the f of x, the outer function, that's basically the function that you have, sorry, in the normal derivative rule. It's the function that you have where you just have an x, right? And then the inner function is the function that is in place of the x. So I'll write another derivative rule. So we know the derivative. Oops, sorry about that. So we know the derivative of sine of x is cosine of x. So the chain rule version of this, I would have derivative of sine not of x. So you use the chain rule whenever you have something other than just an x there. So it'd be sine of g of x. And the derivative would be cosine of g of x, but then because I don't just have an x there where I would normally have an x, I have to multiply by the derivative of that function that's there instead of the x. So I'm gonna go ahead and write the other trig rules right now, but just I'll do it live. I mean, I'll record this. I was gonna like not record myself writing them, but I will. Ah, my goodness. So derivative of cosine, we know is negative sine. So the chain rule version of this, I feel like I'm gonna run out of room. I mean, I'm like on the right side of this thing, because think about like the derivative of secant, derivative of secant, kind of long. So, and then when we add the chain rule to it, that means we're always including this times g prime of x. So notice I'm just using my regular rule, but then I'm also always multiplying by g prime of x. So if you don't really understand or recognize a composite function, the main thing you want to keep in mind when you're working with the chain rule is that anytime you use a rule, if there is some function there instead of your x, like where you would normally have an x, like in the rule you just have an x, but but you have some function in place of that x, that tells you use the chain rule, which means multiply by the derivative of that function that's there in place of the x. So go ahead and write the other trig function rules. So derivative of tangent is secant squared x. So the chain rule version of this, instead of just tangent of x, I'll have tangent of g of x And so I'll have secant squared g of x, but then chain rule says multiply by the derivative of g of x. And then we just have how many more rules? Secant, 3 more rules that we covered so far. Cosecant. Oh, this is all slanted. And then cotangent. So, and then this is the one I'm worried I'm going to run out of room because the derivative of secant is secant x tangent of x. So the derivative of secant of g of x is secant of g of x tangent of g of x. Yeah, I have room. And then times because I don't just have an x there, I have a g of x. Multiply by g prime of x. So because it's not just secant of x that I'm taking. This one I have less room, so I have to be more careful. So those are basically the rules that we've learned so far, and then their chain rule equivalents. So we'll be learning more rules as we go on in this chapter. And so just remember that they'll have like a chain rule equivalent. So now let's look at some problems. This is section 2.4, problem number 2, and it gives us this function f of x equals 5 times negative 5x to the 8th minus 9x cubed, all raised to the power of 18. And it's asking us to find the derivative. I just wrote this down, but like just looking at it, like you might recognize, you might see a power, right? And recognize that you're going to be using the power rule. So you're going to bring that power down. And then take 1 away from your power. And the chain rule says that after you've done that, you then have to multiply it by the derivative of whatever was being raised to the power. Because we don't just have x raised to the power, we have all this other stuff raised to the power. So going to the iPad, we'll work this out on the iPad. Oops, you know what? I think you're already on the iPad, aren't you? Sorry. I thought that I was sharing the screen, the canvas, but I wasn't. But here's the original problem. And I was like drawing on something. So maybe like whatever I was drawing on wasn't making sense, but here's the original problem. So I'll just go back to the iPad now. So we're going to use the product rule as in bring down this 18. So we'll have 18 times 5 times negative 5x to the 8th minus 9x cubed raised to the power of 17, right? So I just used the power rule, and chain rule says, oh, wait. It says I didn't just raise x to the power of 18. Like it wasn't like this function was not 5x raised to the power of 18. If it were just 5x raised to the power of 18, then I could say the derivative of this would be 18 times 5x raised to the power of 17, and I'd be done. But because I have something other than just an x that's being raised to the power of 18, I have all of this stuff being raised to the power of 18. I have to use the chain rule, which says then you multiply by the derivative of all of that stuff that was being raised to the power of 18. So now I like bring the 8 down. 8 times -5 is -40. And then I have x, take 1 away from my power to the 7, minus, and then I bring my 3 down. 3 times 9 is 27. And then this is, oops, I didn't write my x. And then take 1 away from my power, so I have 27x squared. And they tell you not to expand it, so you can just write out the answer like this. I'm gonna go ahead and just multiply the 18 times 5, and then I'll leave everything else. So so then just enter it just like this. So going back to, sorry. So we have 90 -5x to the 8 minus 9x cubed quantity raised to the power of 18. Oh, 17, because I'm taking 1 away from the power. And this is multiplied by the derivative of -5x to the 8th, which is -40x to the 7th, minus 3 times 9, which is 27x squared. And that's what I had written, right? Yes. So they say you do not need to expand your answer. I think they're saying like, please don't expand it like I do. I don't know why that x is in that square is in parentheses. I must have done that accidentally, but it still marked it correct. So let's look at another one. Let's look at number 3. So notice this is a square root function, which means once again we have a power rule situation. Because remember, square root is the same thing as raising to the power of 1/2. So we're gonna just rewrite this first of all as 8 times 7x cubed plus 9x to the 5th, all raised to the power of 1/2. That 1/2. So, and then from here, we'll go ahead and we'll use our chain rule along with our power rule. So power rule, remember the exponent drops to the front. So we'll have 1/2 times 8, 7x cubed plus 9x to the 5th. Take 1 away from your power, so we'll have 1/2 minus 1. And then chain rule says you're not done because you used the power rule and you didn't just raise x to the power of 1/2. It was 7x cubed plus 9x to the 5th raised to the power of 1/2. So because of that, because it wasn't just an x being raised to the power, we have to use the chain rule, which means multiply by the derivative of this thing, which is 21x squared plus 45x to the 4th. By the way, I posted a proof of the chain rule in modules under proofs. So if you want to look at the proof, it's really nice proof, and it's really kind of fast, and it also uses the alternate definition of the derivative, which I haven't used for any of the proofs so far, so it's nice. 1/2 of 8 is 4. So I have 4 times 7x cubed plus 9x to the 5th raised to the power of -1/2, and then times this 21x squared plus 45x to the 4th. And then I think the problem, they ask you not to use fraction exponents. So we'll go ahead and use these rules from algebra again. This one, first of all, that if you have a negative exponent, you can rewrite it as positive by sticking it in the denominator. So we'll do that. And then second of all, what we already used, which is just that the square root of a is the same thing as a to the 1/2. So just keeping all that in mind, we can say that this is 4 times 21x squared plus 45 x to the 4th over 7x cubed plus 9x to the 5th raised to the power of positive 1/2. So I make the exponent positive by just sticking it in the denominator. It doesn't really look like an exponent there, does it? Let's see if I can write it smaller. There, I think it looks more like an exponent there. And then, so everything else gets to stay in the numerator. And then one last thing is they don't want fraction exponents, so I just rewrite this as a radical, as a square root. And there we are. This is it. This is the answer. And I will go ahead and enter that, make sure it's correct, and then we'll look at another problem, and then another problem. So 421x squared plus 45x to the 4th. Oh, that's how I ended up with the parentheses before. And then this is over the square root of the 7x cubed plus 9x to the 5th. The same thing I wrote earlier, just making sure. Okay. And there we go. So no fraction exponents, no negative exponents, so we're good. Let's look at number 4. So notice for this one, we have e involved. And so you want to remember that e, the derivative of e to the x is just e to the x. But in this case, we don't have just an e to the x. We have e to a whole bunch of other stuff. So, so we're about to use the rule that the derivative of e to the x is just e to the x. But again, we don't have just an e to the x, we have e to a whole bunch of other stuff. And so the chain rule tells us that we're going to have to multiply by the derivative of all that other stuff. So let's go ahead and find our derivative. So we'll have, we have a constant, just bring it along. So we have 5e to all this stuff. And then you're like, oh, but that's all this stuff. It's not just e to the x. And so chain rules like, okay, you got to keep going because I don't just have an e to the x there. I have e to all this other stuff. And chain rule says I have to multiply by the derivative of all this other stuff. So, so this is where I bring my exponent down. -9 times 6 is -54. X, take 1 away from the power, the 5th, minus 2 times 10 is 20. And then I have x to the 9th, and I'm done. And just enter your answer like this. So let's go ahead, enter the answer. So what was it? So 5e raised to the power of -9x to the 6th minus 2x to the 10th times -54x to the 5th minus 20 x to the 9th. Is that what? Oh, keep doing that. Make sure that's what I wrote earlier. I like to like redo it just from scratch when I'm typing it in because I want to, that just decreases the chances of making a mistake, you know, like if I do it twice. So, and then I check to make sure that I wrote the same thing because I don't want to like have a written mistake. Or I mean, if I do have a written mistake, I want to go back and correct it. So there's no confusion. So let's look at number 5. So we know that the derivative of sine of x is cosine of x, but notice we don't just have sine of x, we have sine of x cubed, which means we're gonna have to apply the chain rule again for number 5. So number 5, we're using this rule that the derivative of sine of x is cosine of x. But anytime you're using a rule and you have something other than x where the x in the rule is, that tells you you have to use the chain rule and multiply by whatever is there instead of just the x. So in this case, I have sine, so I know its derivative is cosine, right? But notice I have cosine of not just x, cosine of x. I'm sorry, I don't have sine of just x, I have sine of x cubed, which tells me I have to multiply by the derivative of that x cubed, which is 3x squared. And there's my answer. I'm gonna just rewrite it in a more pleasing, aesthetically pleasing way. So 3x squared times cosine of x cubed. Although if you enter it the way that it's written above, that's also totally correct. It's more common to write it the way that I just wrote it. So I'll enter it like that. So 3x squared times cosine of x cubed, close my parentheses, and I'm done. And then when they say find f prime of 1, I say just copy this and paste it. Actually, you know what? It's not, this one's not bad, but you can totally copy this and paste it and then replace your x's with 1s and you'll be fine. The reason I was saying this one isn't bad is because because we just have like 1 cubed is just 1. So it's not like a lot of work to actually just kind of simplify this, you know? So like I would probably actually enter the answer just 3 cosine of 1, but because again, 1 is just an easy number, right? But if you have something like a 15 or something like that, you might not want to deal with cubing the 15. So up to you. Ooh, number 6, you try this one. Try number 6 on your own. Let's do number 7 and then we'll look at number 1 and then well, actually let's do number 1 first and then we'll look at number 7 and then if you have any other questions, come to our work session and ask the questions. So for this one, it says h of x is equal to f of g of x. This is number 1. And it asks us to find h prime of 4. So what you want to do here is use the chain rule because like notice this is set up like exactly the way the chain rule is set up. Like f of g of x. Like that's exactly how I wrote the rule. Here, let me just show you. You see how I wrote the rule? Derivative of f of g of x, right? And is equal to all this, f prime of g of x times g prime of x. So we can straight up write the rule right there. So for this problem, when it's asking us to find h prime of 4, we can say right away, before we do anything, we can say that h prime of x, we know, is equal to f prime of g of x times g prime of x. I'll put a little times here. Times g prime of x. So that is the rule. So so in this case, we're trying to find h prime of 4, right? So we will need h prime of 4, which means I need to replace my x's with 4's here. So this is going to be f prime of g of 4 times g prime of 4. And then from here, I'll use the table to get these values. So for example, g of 4, like when I'm looking to find g of 4, this right here, I'm gonna go to my table. So right now I'm just looking at finding g of 4, right? So I'm gonna go to my table, and I guess I need to see more of the table. I need to see where the 4 is. There. There, I can see the 4. So I notice when x is 4, right here, g of 4 is 2. So in place of this g of 4, I get to put a 2 there. And then on the outside, I still have my f prime. So I'm just bringing that down, my f prime. And then one other thing is I can right now work to find out what my g prime of 4 is. My g prime of 4. So what color shall I use? So many choices. So now I'm going to look to find my g prime of 4. And again, right here we have 4, and g prime is 3 right there. So this will be f prime of 2 times 3. And then now one other thing I can find is my f prime of 2. Or one other thing I need to find, actually. And so I notice that my 2 is right here, and f prime of 2, it looks like, is 3. So I end up getting 3, and then I have times 3. I'm just bringing this 3 down from above, and 3 times 3 is 9. So it looks like my answer, my final answer, let me put equal signs. Equal signs. Equals, my final answer is 9. So that's it. That's for number 1. Using the chain rule. Kind of like really directly using that rule. And then let's look at one last problem. And again, if you have questions about other problems, come to our work session. Let's look at number 7. So this one, I just wanted to look at this one because it's kind of written differently. So same thing with number 8, written differently, but you try that one. So big F of x equals little f of x to the 4th, and big G of x is little f of x quantity to the 4th. And then we're given all this information. So, and we're asked to find like big F prime of A and big G prime of A. I wrote all the information down, and our job is to find, they're asking us to find big F prime of A and then big G prime of A. And so first I just wanted to find big F prime of X, and just in order to like use that chain rule first, and then we'll plug A in. So just like the problem that we did that had sine in it, we found sine of x, the derivative of sine of x cubed first, and then we plugged the 1 in. So we'll do the same thing here. So I'm going to first find big F prime of x and then plug in my a. So all that said, we're told that big F prime of x is equal to little f of x to the 4th. And so chain rule says, like, if you go directly to the chain rule, which I'm trying to get to right now, boxed right here, like, notice this is f of something, g of x is f prime of g of x, that's what I have here circled in blue, times the derivative of g, or g prime of x. So in this case, I have f of x to the 4th, right? So my derivative will be f prime of x to the 4th, and then times whatever is here instead of just an x, which in this case is, I'm sorry, times the derivative of what's there instead of just an x. So what's there is an x to the 4th, and the derivative is 4x cubed. And so f prime of a will be equal to, so I'm just going to replace my x's with a's here. So f prime of a to the 4th times 4a cubed. And then they like give us a bunch of information so that we can find out the numerical value. So like we're told that f prime of a to the 4th is equal to 5. So we can replace all this with a 5. And then we have times, I'm just bringing my 4 down. And we're told one other thing. We're told that a cubed is 9. So we'll replace the a cubed with a 9. So this is 5 times 4 times 9, which is 180. And we're done. So let's do the g prime of x next in order to find g prime of a, which is the next thing they asked us to find. So notice in this case, for the g of x, we have all of this stuff raised to a power, which means, once again, we're using the power rule, but because we don't just have an x raised to a power, we have to multiply by the derivative of what is being raised to the power. So, and just like with the f, I'm going to find g prime of x first. So, and then plug in a. So using my power rule, power drops down to the front. So I get 4 f of x cubed, quantity cubed. And then chain rule says, okay, now you need to multiply by what it was that was being raised to a power other than just the x. So I keep forgetting to say derivative of whatever it was that was being raised to a power. So we have to multiply by the derivative of that f of x that was there instead of just an x. And so the derivative of f of x is f prime of x. And then from here, we replace everything with a's. So we will have 4 times f of a cubed times f prime of a, replacing all of our x's with a's, which ends up giving us 4 times, and they tell us that f of a is 3. So I can replace my f of a with 3. So 4 times 3 cubed times f prime of a, which they give us is 10. So I can replace that f prime of a with 10. So 3 cubed, I know that's 27 times 10 is 270 times 4, I don't know. Let's see, 27. I know 27 times 2 is 54. Here I just used a calculator. So I get 1,080. And this is our answer. So I'll enter both of the answers and then that's it for this section. I believe this was 180 if I remember correctly. Let's see if I remember. Yeah. Okay, take care. Bye.